Hi, it's Rayma. Today it's my pleasure to introduce our work about air pollution sensing on behalf of my co-authors from both Tsinghua University and Carnegie Mellon University. Our work focuses on the fine-grained air pollution inference with mobile sensing systems, where we're using the weather-related autoencoder model. According to WHO, air pollution causes 7 million premature deaths per year, which is a severe global health threat. These facts emphasize the importance of fine-grained air quality monitoring, which could benefit the daily protections for city residents, while also support accurate air quality control and effective city management. Nowadays, static stations and mobile systems are both applied for urban air quality sensing. Official air quality stations are usually deployed statically in many countries for routine monitoring. However, these high-accurate instruments are with great cost, box size, and high environmental requirements. They can barely be deployed with sufficient density to capture the fine-grained pollution map. In recent years, mobile sensing networks are proposed as a supplementary method by a series of previous work. They utilize air quality sensors with lower unit price and further motivate them by carriers like human and vehicles to achieve wider range and greater granularity. Although mobile sensing provides higher possibilities to capture detailed variations, the samples are still unable to cover the entire spatial temporal space. An inference algorithm is still essential to recover the fine-grained air pollution map, therefore supporting a comprehensive understanding of the city environment. Previous algorithms for air pollution inference in traditional area are mostly based on deterministic models describing physical and chemical processes. However, these models require abundant prior knowledge like initial states and pollution sources, and suffer from great computation complexity. With growing amount of observed samples, data-driven methods are proposed, especially deep learning methods. Nevertheless, deep learning models are always seen as black boxes, and the selection of these models is scarcely backed up with physical interpretations. On the other hand, samples from mobile systems are irregularly distributed in time and space. Meanwhile, the relative positions among mobile sensors are dynamic. The dependencies in spatial temporal neighborhoods of a pollution map are hard to be learned. Above all, while using deep learning methods in air pollution inference, there are two major challenges. First is the non-interpretability of deep learning methods. These deep learning models without physical insights may have bad extrapolation abilities. And the second is the irregular samples from mobile sensing. Among existing machine learning structures, it is difficult to model the dependencies in spatial temporal neighborhoods directly with the regular samples from mobile sensing. In this paper, we address these two challenges from two perspectives. To provide deep learning methods with physical insight, we first review the physical insights of convolutional long short-term memory system with a classical physical model in environmental fields called atmospheric dispersion model. Then we customize the convolutional LSTM with a weather-related kernel in its inner structure, which introduces auxiliary information, and it also connects the daily pollution inference models, which enables the algorithms to be quasi real-time. On the other hand, we address the irregular sampling from mobile sensing. Previous data-driven algorithms are mostly inferring unobserved samples directly from observed ones. A typical kind of method uses a temporal spatial predictor to learn the relationship among a group of fixed samples. However, since the relative positions of samples are dynamic in mobile scenarios, this kind of inference cannot fit into our problem. We address this challenge by introducing the autoencoder framework from image denoising. Therefore, it separates the pollution reconstruction process and sampling process. Instead of directly modeling the relationship between observed samples and unobserved samples, this framework first compresses information from the observed samples into a low-dimensional latent vector, then reformulate the whole pollution field. And after that, by imitating the sampling of mobile systems, we could evaluate the inference performance using our irregular samples. In order to evaluate our proposed algorithm, we deployed a real-world data collection in a coastal area in Tianjin, China within half-year time. The sensing units were installed on 8 static sites and 15 mobile sites. By comparing with existing methods, our method obtains 15% less error and 7% higher correlations than the second place in offline applications, and achieves 4% less error in quasi real-time applications. Benefited from the physical insights, our algorithm also achieves higher robustness against bad conditions like low sampling coverage and bad weather. Here are the conclusions, including 3 contributions. Due to the limited time, please find more details in our full paper. Thanks for your listening.